In this lecture, I'll discuss how to generate a magnetic field. As we discussed in a previous lecture, moving charges generate magnetic field. In our unit on motion, we described two different types of motion, translation and rotation. Charges undergo rotation within atoms. Electrons, the negative charges in atoms, are constantly spinning in their orbitals, which are their positions within the atom. Charges undergo translation when they're simply just moving through space, or most often we'll be dealing with charges moving in a current. First, let's work on calculating the magnitude of the magnetic field B generated by a current I flowing through a wire. So, this is called the Biotavart Law. This law states that the magnetic field generated by a current flowing through a wire is equal to a constant mu naught divided by 4 pi times the magnitude of the current times the length of the wire divided by r squared. This is the distance of the point from the wire, so this is where we're testing, the point at which we're testing the strength of the magnetic field. Since B is a vector, we know that there has to be a direction of the magnetic field. So what is this direction? We have to now introduce a concept known as the Righthand Rule, often abbreviated as RHR. Here's a nice diagram of the Righthand Rule. Basically, the Righthand Rule states that if you wrap your fingers, pointing your thumb in the direction of the current, I, mind you, this is the conventional current, the flow of positive charges, your fingers should wrap in the direction of the magnetic field, which will look like this line here. And you will also see concentric magnetic field lines outward like this. So together the magnitude and direction comprise the vector magnetic field. Another aspect of calculating magnetic fields we should talk about is the constant mu naught in the Biotavart Law. This constant has a lot of fancy names, such as the vacuum permeability, or the permeability of free space, or even the magnetic constant. Basically, this constant describes the ease with which a magnetic field can permeate a vacuum, which is free space. If you eliminate this zero, the naught part of mu naught, you end up with just mu, which is another constant that can be used to describe the permeability of another type of medium, such as the air or a metal or something else. The value of mu naught is 1.256, this is approximate, times 10 to the negative 6th, and the units here are Tesla times meters over amperes. Amperes is a unit of current. In our next lecture, we'll talk a bit more about how a magnetic field is generated by a magnet.